Hello again. For starting off this week, we'll start with moving through the rest of the cardiovascular system, which is basically the heart, the blood vessels, and the lymphatic system. So we're going to talk about we did the heart last lecture, so we're going to do the blood vessels this time. Circulation. Okay. If I can get it, there we go. So the last time actually a couple of times now, we've gone through this sequence where the blood comes in through the vena cava, right atrium, and so forth and so forth and so forth. When it actually goes out to the body, though, it goes through several different kinds of vessels that are designed to do different jobs everywhere they go. You have the arteries, the aorta. We've already seen the aorta, aortic arch. It goes over. It has its coronary arteries coming off of that. And then it starts sending out large arteries to main body parts. You've got a couple that go up to your brain. You've got a couple that go into your arms. The aorta itself goes all the way down through the thorax and into the abdomen. And you keep having blood vessels go off of that to the kidneys, to the liver, to the stomach, and then down into the legs. And so those are considered the large arteries, and they're the size of a pencil or something like that. And so the blood pressure in them is very similar to that in the aorta, and therefore when you're taking your blood vessel at your arm, blood pressure at your arm, you're getting about the same pressure that you would get in the aorta. So that's what that's all about. But those are just designed to take the blood places. They have to go into smaller and smaller vessels until you get ones that are so tiny they can allow nutrients and oxygen to exchange with the tissues. And then you have to bring it back. So that's where we're going now. Then back, it all dumps back into the vena cava and back into the right atrium and starts over again. So here we have arteries and veins. Arteries always go away from the heart. Veins always come back. Arteries are high pressure vessels. When the blood first leaves the heart, the pressure is quite high, and it drops and drops and drops and drops and drops and drops until it gets back to the vena cava, which is almost zero, and that gives you the pressure gradient to push it out of the aorta and bring it back in through the vena cava. So high pressure arteries have thick walls. This tunica is a connective tissue. It's very elastic. It's like a piece of surgical tubing. It'll stretch and recoil. Inside of that you have a muscle layer, which allows especially the smaller arteries that are more controlled instead of just taking stuff there to squeeze or open. Because you may not want blood going to your legs as much while you're sitting down. You might need more blood going into your stomach to digest food or into your brain because you're doing some thinking. But when you run, they have to open up. So you have to have the ability to close and open these blood vessels. Lined with a simple squamous epithelium on the inside, lots and lots of receptors, the ability to interact with the blood, and also to protect the layers that are beneath it. The veins are similar, except the pressure is lower, so the walls are thinner. The lumen, which is the hole in the middle, is bigger. And because the pressure is so low, it would be hard to get the blood to come back from your feet. There's not enough pressure to push it all the way back up to your heart against gravity. So you have one-way valves. So whenever any blood goes past the valve and then tries to come back, it stops. So blood is only allowed to move in the direction of the heart. So if you walk and your muscles squash the blood vessels, it moves the blood back toward your heart. If you squeeze some of the smooth muscle here, you squeeze the veins, the blood will always move in the direction of the heart because the valves won't let it go the other way. Here's the typical size. Here's the aorta, or a big artery anyway, where you have a relatively small lumen with a thick wall, lots of muscle, lots of tunica. Here you have the vena cava, which has a thicker wall and a bigger hole in the middle, a bigger lumen. And everything in between, arterioles, capillaries, and venules. And we're going to talk about these separately. The capillaries are so small that they don't even have anything except the simple squamous epithelium and a very porous membrane around it, and give them some strength so that they don't just pop. But it allows everything to go in and out that you need to go in and out. It doesn't have muscle like this here, or a tunica on the outside like that. Blood and fluids and things can't pass through these guys. It only really passes through capillary walls. So here we have blood from the heart. It goes, the aorta goes big arteries, smaller arteries, smaller arteries. It gets down to the arterioles, which are these blood vessels here that have nothing but muscle around them, because they really give you a chance to close the blood flow to that particular tissue, or allow a lot more if you want them to. They have a lot of little smooth muscle cells wrapped around them, so they can squeeze or open, or squeeze or open. From them, you have the capillary beds leading off. And at the proximal end of each capillary, you have what's called a precapillary sphincter. Gives you one more chance to control blood. If I don't want blood going right here, but I do want it going here, I can close this precapillary sphincter and shut off that tiny bit. Not all of your tissues need a lot of blood all at the same time. A lot of it's intermittent. It opens, makes sure they're okay, it closes again so blood can go somewhere else, and then it opens again, closes again. And then it moves across the capillary beds and into the venule, which has a little bit of ability to open and close to control the outflow flow. And then that flows back to small veins, bigger veins, vena cava, and back to the right atrium. So each of these types of blood vessel has a different job to do, so we can organize them by what they do. A big tube that's just mainly designed to take blood straight to someplace is called a conduit vessel. Your aorta, your large arteries, your vena cava, these are big tubes that are taking blood from here to here. Now they also, as we'll see, they stretch when your heart beats and then recoil afterward, and it helps smooth out the blood flow instead of it just pulsing real powerfully, all on and all off. Instead, it's a little bit smoother process, as we'll discuss later. But conduit vessels are the large arteries, large veins, the vena cava and the aorta. Resistance vessels are primarily your arterioles. Arterioles have nothing but muscle around them, so they can close when you don't want blood to go through them and open when you do. The venules have some resistance also, but mostly it's your arterioles. Those are leading into the capillary beds. So these decide how much blood is going to flow through a particular capillary bed, and that's where exchange takes place. Capillary walls are so thin, gases can move back and forth, oxygen and CO2, fluid can move back and forth, nutrients can move back and forth. So the capillary beds are where all of the exchange of nutrients and gas and stuff takes place. Now you move back from the capillary beds into the veins, and the large veins they're very thin walled and they stretch real easily. So if you have blood that you don't need whooshing through your circulation right now because you're at rest, those blood vessels will relax, stretch. With still low pressure inside, they will have the capacity to hold that extra blood. When you start exercising, they squeeze and push it back toward the heart. But during rest, they have the capacity to hold your extra blood volume. It doesn't stop moving, but it slows way down and just kind of moves slowly through there, and then speeds up when it gets back to the heart. These are your large veins. Large veins in the legs and in the trunk have the capacity. Those are capacitance vessels. Then we have shunt vessels. A shunt vessel allows blood to go from an artery to a vein without exchanging anything. So let's say I get a cut and I bleed some. I need more blood coming back to my heart so I can supply my brain and stuff, because suddenly my blood pressure has dropped. I don't have as much blood. I have vessels that will open and allow that blood that was going to go to my foot to cut across and come right back. No exchange takes place. You're just getting it back to where you need it more quickly. Those are shunt vessels. They're also called, and we'll see this term, anastomoses. Anastomoses are shunt vessels. They can open up and let blood pass across. Here's their diameters. The aorta is the size of a garden hose. Large arteries, anyway down to 1 millimeter, which is pretty small, but small arteries go way smaller. And these are conduit vessels up here. Pulse dampening, but distribution, conduit. The arterioles are resistance vessels, really small, 1/100th of a millimeter. Capillaries are much, much smaller yet. You have 6/1000ths of a millimeter. This is where exchange takes place. Then the venules are about the same size as the arterioles. The veins are a little bit bigger, and then the vena cava. You can see the vena cava has a bigger hole than the aorta, because the aorta has a thicker wall. Vena cava is your actually largest diameter vessel you have. All of this blood comes back through the vena cava to reach your right atrium. Arteries deliver blood and dampen pulse. See, here's an overview. Here's a cheat sheet. Arterioles, resistance, open and close to allow blood. Capillaries, exchange, exchange, exchange. They're the only exchange vessels you have. Veins, thin, stretchy walls, one-way valves. They keep blood moving in the right direction even though the pressure's low. Capacitance vessels. They hold extra blood during rest when it isn't needed elsewhere. And so your cardiac output is the amount of blood your heart pushes out per minute. Stroke volume, the amount of each beat times heart rate, how many beats there are in a minute. That will, this times this gives you your cardiac output. It comes out in one place. It goes out through the aorta and it comes back in the vena cava. But in between it splits and goes everywhere. It goes to your brain, it goes to your eyes, it goes to your stomach, it goes to your legs. Okay? And it doesn't go first to your stomach and then to your liver and then to your spleen and then to your intestines. It goes to the stomach and then back to the veins. And another secondary little circulation comes off that aorta and it goes to the intestine, comes back to your veins. So you have a bunch of individual circulations designed to supply each part of your body, individually controllable. So when there's no food in your stomach, you don't send as much blood to your stomach by controlling that flow, and you send more of it somewhere else. So the blood flow in each little circulation is matched to that body's tissue needs, that tissue's needs. So here a stupidly simple version of it says the left heart pumps it out the aorta. It's stretchy, so it helps dampen the pulse, but it goes to the large arteries and gets down to the arterioles that control the flow. And then you've got all these different tissues. Each one can give however much blood it needs to. It sends the blood back to the veins that have one-way valves in them, comes back to the vena cava, goes in the right atrium, then it goes through the lungs to get oxygenated and starts over again. At rest, about 2/3 of your blood is in the veins and only 1/3 is in the arteries. The arteries are strong. Unless the pressure is pretty high, they're not stretched open very far. The veins are soft, so they stretch. You don't need that much blood going through your tissues at rest. During exercise, you might need 5 or 6 or 7 times as much blood per minute going through the arteries. So you get it out of those veins and push it into the arteries. the pressure's higher, it stretches those arteries open, and more blood is over there. But during rest, 2/3 of the blood is kind of hanging out in the veins. As I say, it doesn't stop. If blood stops moving, it likes to clot. So what you want it to do is keep moving, just not very fast, and then speed up when it gets to the arteries, and then slow down. It's like being in a ski lift line or a Space Mountain line at Disney World, where you never stop. You just kind of trudge along, and you finally get to the ride, and then you go really fast for a while, and then you come back and you move, and then you go really fast for a while, and then you move. So that's kind of the way it is. Most of the blood is hanging out in the veins during during rest. When exercise happens, you increase that venous return. You squeeze the blood vessels, they contract their own blood, muscular walls. You know, the ways that we talked about in previous lectures about increasing venous return brings more blood more quickly to the heart so that the heart has more blood to push out. And it also stimulates the heart to beat faster and stronger. Funny looking graph here. You're going to have a bunch of them in this lecture. Here we have, at any one moment at rest, how much blood is in the various blood vessels. Well, the aorta has a little because it's that wide. You get to the large arteries, there's a little bit more at any one time in there because they're not as big as the aorta, but there's a lot of them. Arterioles are little squeezy guys. There's not a whole lot in them. They're real short. They're like a valve, so there's not a whole lot of blood in those at rest. But your veins have a lot of blood in them. This is where most of your blood is. Major venous branches, large veins. Then you get back to the vena cava, which itself is quite short. All the venous blood comes into it, but it's bigger around than the aorta, so it actually can hold a little bit more blood. Typical blood volume in an average human is about 5 liters. 6 liters in somebody that's pretty big, maybe even 4 in somebody that's really small, somewhere around 5 liters of blood, which is a good number that we use as a default if we have to do a calculation. 5 liters. Pressure in the arteries is high, 120/80. These are millimeters of mercury of pressure. A millimeter of mercury is how high mercury will go up in a barometer when you push on it. Okay, so a certain amount of pressure will move mercury 1 millimeter. That's a millimeter of pressure, a millimeter of mercury. So 120/80 is pretty high pressure. Like we can say that the mean arterial pressure is fairly close to 100 in a typical resting person. At the capillaries, it has dropped down quite a bit. You go from high pressure to lower, to lower, to lower, to lower, to lower, to lower. That's what keeps the blood moving the right way. Capillary pressure, it starts out around 32 and drops down to about 15 as you cross through the capillary beds. At the vena cava, you're getting down to pretty low pressure, very close to 0. So while, this is 120/80, if you actually figure out mean arterial pressure, it'll be somewhat different than 100. And if you figure the pressure in the vena cava is not 0, because it's got to be enough to flop it into the right atrium. But we can say, generally speaking, mean arterial pressure in the aorta is around 100. At the vena cava, it's close to 0. That's the pressure gradient you have to move the blood from the aorta all the way through your system and back to the vena cava. Another term which is commonly used in medicine is the mean circulatory pressure. And this means not angry, but average. Average circulatory pressure. Let's say you've got a lot of blood in your low pressure veins. You got a little bit of blood in your high pressure arteries. This is high, this is low, everything in between. If you balance it all out, about what kind of pressure do you have? It's only around 7 millimeters of mercury is a typical mean circulatory pressure. So, if somebody's bleeding out, their mean circulatory pressure drops down to 5, they could be in trouble. You give them an infusion of plasma or something, it goes back up to 6. You've increased their mean circulatory pressure. This is a useful term to know what you're doing. It's affected by the volume of blood. So if you bleed out, it goes down. If you retain too much water, it goes up. It goes up during exercise. Sympathetic stimulation causes everything to squeeze. You move a lot of blood out of those low pressure arteries into the high veins, into the high pressure arteries, from the low pressure veins to the high pressure arteries during exercise. So now more blood is under higher pressure. Your mean circulatory pressure goes up and up and up. And you need it to during exercise. You got to move that blood. Here's a law you're supposed to understand. Fortunately for you, I don't make you do this calculation. It's not as bad as it looks. This is cardiac output, should have a dot over the top of it, but the flow of blood through any tube is equal to these factors divided by these factors. Now here's pi is a constant, and so is 8, so you can ignore those guys. Pressure, if you double the pressure, this is on top. So if you double the pressure, it's directly proportional. Twice the pressure will double the flow. This little funny looking N down here is viscosity. This is how thick your blood is. This is on the bottom. If I double the thickness, I'll cut the flow in half. Inversely proportional. Okay? L is the length of the tube. If I put a second garden hose on my first garden hose of equal length, it will cut the flow in half because of the resistance along the walls. That's not a big deal for us. Our blood vessels are always the same length. So what factors are we going to change our blood flow? Well, you can increase pressure, but we're not going to double it. You don't go from 120/80 to 240/160. But, if you increase the pressure, you'll increase the flow. The biggest way that we increase flow is to increase the radius of the blood vessel. In other words, you open it up. Because if I double the radius of the vessel, I will increase flow to the power of 4. In other words, 2 times 2 times 2 times 2. So double in pressure will double my flow, but double my radius will increase my flow 16 times. 2 times 2 times 2 times 2. Good test question. What's the best way to increase flow to a tissue? Open up the blood vessel. Increase the diameter of the radius of the blood vessel. It allows more flow. Now we do change the viscosity of the blood. If we sweat a lot and our blood becomes really thick, our blood gets too thick and the flow slows down. So viscosity is a factor that changes in humans, and these are the ones that are changeable, really. You can change the pressure, you can open and close a vessel, or you can make the blood thicker. So this whole law of Quasi here, for you to understand, is this is important, this is most important, and this is important for controlling the amount of flow. Right. Radius of the blood vessel. So if I go from 4 to 8, I just don't double my flow. 16 times. Goes way up. It's parabolic. It just shows you how important it is to be able to close and open blood vessels to control the flow to the various tissues. That's our main strategy for controlling blood flow to our heart, our stomach, our arms and legs, and whatever. Viscosity, I said, is inversely proportional. So if you double the thickness, honey doesn't flow as fast as water. So if you make your blood thicker, it slows down. So here we have the viscosity. As the viscosity goes up, okay, as that hematocrit goes up, the viscosity goes up. The main factor that controls how thick your blood is the percentage of it that's red blood cells. Now, if you do blood doping, or if you have a tumor that makes too much erythropoietin, and you have polycythemia, your blood will become too thick, and it doesn't flow very well. The other way to thicken it is to sweat too much without replacing it, and your sweat, you lose plasma, and therefore what's left behind is a lot of red blood cells, and it's thicker. Okay? The normal range for hematocrit allows, gives you a viscosity that works. Much outside that range, the viscosity gets too high. Below that range, it drops down until it's only plasma, but within the proper range, you have a livable viscosity to your blood. The next factor for blood flow is the linear velocity. If you have blood going happily through your carotid artery and it involves a blockage, your heart's going to push as hard as it needs to get that blood through to your brain. So through that pinch, it speeds up. If you put your thumb over the end of a hose, if the same amount of water comes out, it goes a lot faster. It shoots. Now, if you close it off enough, not as much will come through, but I'm not talking about that. I'm talking about same amount of blood. If you squeeze a spot, it will have to go faster through that. Directly proportional, or you could say indirectly proportional. The smaller the tube, the faster the blood has to go for the same amount to go through. Okay? So this is important because when blood moves too fast, it can be a problem. It can make noise. It can give you a heart murmur if it's going too fast. It can give you sounds in your carotid arteries if it's shooting through there too fast. So fast moving blood is usually caused by a stricture, a closing off of some part of a blood vessel. So this puts those last couple of things into context. How much cross-sectional area do we have? Because remember, if it's small, it goes faster. If it's big, it goes slower. Small tube, same amount of blood, it's going to have to go really fast. Really, really big tube, it goes slower. Well, what's important is that during that part of the trip, what is your blood encountering? At the aorta, it's a big blood vessel, but there's only one of them. So the blood goes really fast at the aorta because 100% of your cardiac output has to go through the aorta every minute. So it moves fast. As it moves into the capillary beds are we have the largest total cross-sectional area. Each capillary is microscopic, but you have billions of them. It'd be like bundling a whole bunch of straws and wrapping tape around them and putting water through 10,000 straws instead of one garden hose. You have a bigger total cross-sectional area. So the water could slow down as it went through those straws and then speed up again if there's a garden hose on the other side, because you're going through a really big area, that same amount of blood going through there. It's not only going through one straw at a time, it's going through all of them at once. So if you have a single line going into Burger King, but once you get up there, you've got 15 lines, it changes the outcome. So as a result, at the aorta, you have fast 300 millimeters per second. That's a lot, 1001, 1001. That's pretty fast blood flow, 1001. When you get down to the capillaries, there's so much overall cross-section that it almost stops. This gives the blood time to go smoothly through the tissues, exchange all the nutrients that it needs to, And then when it moves back into the veins, it speeds up again and comes back to the heart. Because the vena cava is only one tube also, or two that join at the right atrium. But it's moving faster there because that's not as big a total cross-sectional area as it is at the capillary beds. Total circulatory time is about 60 seconds. So it leaves the aorta, it goes pretty fast at first, and then it slows down. It goes to the capillaries, and then it gets picked up by the veins, and it speeds up and comes back to the heart. About a minute. And this graph always shows up on your tests because it puts all of these factors together. This is another one that looks terrible when you first look at it. But here we have the aorta. We go to the arteries, then the arterioles. What happens at the capillaries, then the venules, the veins, and back to the vena cava? What is the blood doing as it going through there? Well, it's going fast at the aorta. It slows down at the capillary beds, and then it speeds back up when it gets to the vena cava, right? So just look and see. Okay, it's going to, whatever it's lowest at the capillaries is the speed of the flow. Why is that so? Because the cross-sectional area at the capillaries is the highest. High cross-sectional area gives you low velocity. So the cross-sectional area at the aorta is low. That's why the blood's moving pretty fast. Cross-sectional area goes up. Big cross-sectional area in the capillaries, so the speed is really slow. Then as the cross-sectional area drops down toward the vena cava, your velocity speeds up again. What about blood pressure? It's high here, it's low there. It never comes back up again. Your pressure drops the whole time to keep your blood moving the right direction. What's this guy? Well, what is greatest in the veins? The percent of your blood volume at any one time is highest in the veins, right? So you look at the black line here and you'd say, what is the highest in the veins of any other kind of blood vessel? It's got to be where your blood's hanging out. So the percent of blood volume. So go through this and look through here and see which line would tell you what based on what's going on at the blood vessels. Like I say, this usually shows up on a test about blood. Look, an overview slide. A lot of students like these. Gives you a chance to go through it. If you don't understand something, go back and look at that slide again. Post something on the discussion board. Ask about it. You know, don't fret over a topic for 2 hours trying to figure it out. Put a question on the discussion board and let somebody answer it for you. It'll be good for them. It'll be good for you. So the control of the blood, the control of local blood flow, these are all individual circulations coming off of the aorta. You know, the first you have carotid arteries going up into your brain. You've got your coronary arteries leading into your heart. You've got the hepatic artery leading into the liver, renal arteries leading into the kidneys, and they will distribute the amount of blood that tissue needs, which changes during exercise, but at rest, you know, your brain gets about 0.7 liters, your heart gets about 0.2, so there's about a liter of your blood. Your liver and your digestive tract get about 1.35 liters. It's a pretty decent amount. More if you're digesting a big meal. It might squeeze down some of these others, and you might get a little sleepy because more of your blood's going through the liver. Your kidneys always get about a liter. About a fifth of your blood flow goes to the kidneys to be filtered. Skeletal muscle, about a liter at rest, but it can go up 4 or 5 times that much during exercise because you dilate those arterioles and you let a lot more blood go through the skeletal muscle. Skin, not very much, but a lot more if you're sweating a lot. Bone and bone tissues. You don't need to memorize all these, although it's good to remember where your main cardiac output's going, your brain, your liver, your kidneys. skeletal muscle being very changeable. Control of flow. How are you going to control it? Well, the systemic stimulation is autonomic nerves, sympathetic nerves, parasympathetic nerves, fight or flight, rest and digest. You're going to deliver blood to working muscles, skeletal muscles during exercise. You're going to deliver it to the GI tract during rest and digest. Mostly we're using GQ proteins, vasoconstriction, GQ, which releases calcium inside the cell, causing vasoconstriction. Parasympathetic will tend to use nitric oxide to cause vasodilation. And then local control wins every time. If you start running and your blood vessels squeeze to raise your blood pressure, so you got plenty of pressure, that sounds counterintuitive. It sounds like you would reduce blood flow. No, what you do is increase pressure so it's moving faster, and then locally you dilate the blood vessels that are asking for oxygen right then. And that high pressure blood goes there. So local control, we will produce vasodilators and vasoconstrictors based on what that tissue says it needs. Sodium, calcium, potassium channels stimulated by signaling molecules. If you stretch a blood vessel, it tends to recoil. Voltage changes, you can cause action potentials to occur. A lot of local control goes on inside these blood vessels to make sure that the tissue that's asking for that extra blood will be able to get it. If a tissue needs more blood, it will vasodilate its own blood vessels, and local control wins every time. It'll compensate for whatever systemic squeeze you had that raised your blood pressure at the beginning of exercise. Vasodilators, okay? Adenosine, histamine, nitric oxide, lactic acid will do it some. These are vasodilators that locally the tissue can use. Hypoxia will also cause a relaxing of blood vessels because it causes the low oxygen causing low ATP will cause the vascular smooth muscle, that's what VSM is, vascular smooth muscle, to relax. There's a series of K channels that are sensitive to ATP availability. And if you allow potassium to go into a cell, it hyperpolarizes it, it relaxes. You don't need to know that mechanism. Just know that you can vasodilate by producing vasodilators, but your blood vessels will also dilate just because there's not enough oxygen around. Just by automatically, you'll get vasodilation to make sure that tissue doesn't starve for oxygen. Over the long haul, you can make new blood vessels. It's called angiogenesis. And as you exercise a lot, and your tissues demand more and more and more oxygen, you'll grow more blood vessels and deliver oxygen better to those tissues, including your heart. Increase in metabolic rate will cause an increase in blood flow. So if a tissue is working harder, burning ATPs, burning oxygen, automatically you will dilate to give more oxygen to those tissues. It's almost a direct linearity, as is heart rate. If I double my metabolic rate, I'll double my heart rate up until the point where it can't go any faster. It's a fairly straight line. And this allows us to do graded exercise tests where you run on a treadmill and you graph out what your heart rate is at this level, at this level, at this level, and you can draw a line and, calculate your metabolic rate based on your heart rate. Another thing that happens during exercise to control flow is called reactive hyperemia. Now, active hyperemia means I'm running and I'm getting more blood. Hyper, it means more. Emia refers to blood. Active hyperemia means I become active and I get more blood. Reactive hyperemia means I shut off the blood flow, and then when I reopen it, I get more than I would have gotten before to make up for it. It happens in a lot of tissues. It happens in your heart. When your heart squeezes, it smashes its own blood vessels and blocks its own blood flow. So between beats, they open up some extra so you can get some extra blood going through the heart tissue. You get active hyperemia. Reactive hyperemia. So you cut it off, the reaction is more blood flow until you make up for the time when you didn't have any. It's a fairly common phenomenon, and especially in the heart. One thing we'll see when we get to the blood vessels too, there's a stretch activated or shear activated calcium channels in your blood vessels. When you first stand up, all your blood falls into your feet. If it stayed there, you'd pass out. Instead, you stretch those blood vessels and they just reactively contract enough to push it back up so that you keep the blood up here and you don't pass out. Okay? And in young people, that works really well. Old people, their blood vessels get weak, like other muscles get weak. They stand up, they pass out, they fall and break their hip. It's a fairly common orthostatic hypotension problem that causes older people to pass out. So when this is working properly, you have a stretch-activated calcium channel that will allow the allow the vessel to squeeze back to react to being stretched really fast. The concept of autoregulation. If a tissue does a good job of demanding and delivering its own increase in blood when it needs it and shutting it off when it doesn't, it's considered to be autoregulated. If it lets the systemic circulation do all the work, then it's not very autoregulated. So here we have, like in your kidney. Your kidney, you don't want a whole lot more blood going through your kidney while you're running because you just pee more. All you need is still that 1 liter a minute going through. So when cardiac output increases 5 times, you don't want 5 times as much blood going through the kidney or through your brain and blow your blood vessels apart. So those tissues auto-regulate. They detect the higher flow rates and they shut down to decrease the amount of blood that goes through those tissues. So here, normal range of blood pressures from rest to exercise, renal blood flow stays about the same. Kidneys, renal is kidney, renal blood flow about the same. This means that during normal blood pressures, it is auto-regulating, so it always gets the amount it wants. It's not getting more just because there's more around. Auto-regulation. Kidneys do it really well, so does your brain. You don't want 5 times as much blood blasting through those arteries in your head while you're running. You might want a little bit more if you were getting tired and needed to get out and move around. You're bringing it up to normal then. You're not adding a whole bunch more. Your heart is a good autoregulator because when it works harder, it needs more blood. So it will dilate its own blood vessels to allow it to get as much extra oxygen as it needs to supplement it while it's working harder. Most tissues do it some. Your skin, your sweating mechanism is not auto-regulated. Your skin doesn't regulate its own blood flow. Your skin isn't very metabolically active. It doesn't need a ton of of blood to survive. The flow of blood through your skin is for sweating. So your systemic system, it tells you what your temperature is, and it either sends out more signal to sweat more or less, so it doesn't. So it's not auto-regulated. So if you're asked for a really highly auto-regulated tissue, you'd probably say the kidneys or the brain. If you ask for not auto-regulated, you would say skin. Your skeletal muscle is quite variable. During rest, it's systemically controlled. That basically controls your blood pressure. During exercise, though, it suddenly becomes auto-regulated because it dilates dramatically to let more blood come through during exercise. So skeletal muscle goes from being systemically regulated to auto-regulated during exercise. Last semester, we talked about receptive relaxation with smooth muscle in general. When you eat a Big Mac, your stomach relaxes and then holds the new volume. You eat a little bit more, it relaxes some more and holds the new volume without the pressure being really high. Otherwise, you wouldn't be able to eat more, and you can for a while. Once it runs out of room, then the pressure goes up enough that you stop eating. Okay? That's called receptive relaxation. It relaxes and grabs around the new volume. Relaxes, grabs around the new volume. Smooth muscle does that. Receptive relaxation is something that happens with smooth muscle. Now, this happens especially in your veins, too. Okay? If I add a bunch of volume, if I shot a bunch of blood into the veins, first of all, the pressure would go up, but they would receptively relax. They would receptively relax, and the pressure would go back down some. If I took the volume back out, they would receptively adjust to that. So they're trying to keep it as close to normal as possible. So blood vessels will, when you stop exercising and all your blood wants to move into the veins, the pressure doesn't stay high there. They relax and hold that new volume. Receptive relaxation. Chemical control is one of the main ways that you get local vasodilation and constriction. You make vasodilators when you need more blood, and you make vasoconstrictors when you need less. Okay? What you have are your endothelial cells. This is a simple squamous epithelial cell. Lots of receptors, so it can receive all of these signaling molecules. Here's histamine, and here's thrombin. If you're trying to blood clot, you can cause your blood vessel to constrict so that it won't bleed so bad, and all kinds of signals can cause you to release most often nitric oxide, which is a smooth muscle relaxer. So the endothelial cell makes nitric oxide, and the smooth muscle underneath it relaxes, and you dilate the blood vessel. So that's how here mast cells making histamine. If you have an allergic reaction, histamine is released, and it causes the blood vessels in your eyes to dilate, and your eyes turn red. You get bloodshot. Or in your nose, they dilate, and your nose starts running. Okay, so making vasodilators largely works through nitric oxide to then locally control. So if I start working and my skeletal muscle needs more blood, it will start producing vasodilators and cause its own dilation of blood vessels. And as we know, that's the best way to increase flow, to get more blood to go through those blood vessels. Relaxation, here we have histamine, bradykinin, acetylcholine. Remember, acetylcholine, this is a parasympathetic neurotransmitter. So rest and digest, you might be dilating some blood vessels at times. Okay, we're going to make nitric oxide, and it's going to relax the muscle. You don't need to know all of these reactions. I don't care. Vasodilators, nitric oxide, cause that smooth muscle to relax. You open the blood vessels and you get more blood. So, and you take antihistamines, so your nose won't run. It blocks the histamine. It blocks the production of nitric oxide. Your blood vessels don't dilate so much, and your nose stops running. Some of these histamine receptors, though, histamines, actually, there are several different kinds of receptors that are, Benadryl, Claritin, various other, blockers of histamine receptors. Some of these receptors are also found in the brain, which is why Benadryl in particular makes you drowsy if you take Benadryl. Some of your anti-seasick medications also work the same way. All they are histamine blockers. And so they bind to some of these receptors. Dramamine makes you drowsy. Adenosine is a big vasodilator. Every tissue in your body can make adenosine. Think about it. We have ATP in our cells. They all have a bunch of ATP in them. If you lose a phosphate, it becomes ADP. That's how we get energy. Lose another one, it becomes AMP. Think cyclic AMP. It's when you've lost two. Lose one more, and then instead of being monophosphate, now you're just adenosine. So if you really have no oxygen in the area to keep making your adenosines into monophosphates, diphosphates, triphosphates, to push it in that direction, it'll move in the other direction and you'll have a lot of adenosine. The adenosine gets released into your blood. It binds to adenosine receptors, and they make you make nitric oxide. So it works a lot like histamine. Histamine, prostaglandins, bradykinin, adenosine makes nitric oxide, and this gives every cell in your body the ability to beg for oxygen if it needs to. It can make adenosine. Adenosine will open the or bind to those receptors, nitric oxide, and you'll dilate. Vasoconstriction works the same way, except instead of making nitric oxide, you make something called endothelin. Endothelin 1 in particular, but endothelin from your endothelial cells. And here's some vasoconstrictors. Thrombin, if you want to constrict. Here we have vasopressin, which is antidiuretic hormone. This can be used to raise your blood pressure. Free radicals will sometimes do it. You don't have to memorize that. Although remember angiotensin, too, with your angiotensin-renin-aldosterone system. That causes vasoconstriction. But the mechanism it uses, it makes your endothelial cell make endothelin. Endothelin causes smooth muscle to contract. So vasodilators, nitric oxide, relax. Vasoconstrictors, endothelin, contract. And this allows that tissue to decide how wide that blood vessel is going to be, and therefore how much blood gets to that tissue. There's a few more vasoconstrictor substances. Epinephrine from the sympathetic nervous system will do it. Angiotensin 2 in particular. Vasopressin. Endothelin 1 is the outcome. It causes that muscle cell to actually contract. Okay, an overview slide. I know that was a whole bunch of different concepts. This lecture is probably going to take more moving through a variety of concepts than maybe any of the other lectures in the whole course. The heart is fairly straightforward. It's got a lot of parts, a lot of moving parts. It's got the Bainbridge reflex that makes it beat faster and the Starling reflex that makes it beat stronger. But getting the blood to go where it's supposed to, changes in pressure. Most important is the change of the diameter, the radius of the circle of the tube. And that's where all these vasoconstrictors and vasodilators come in. Vasoconstrictors, not as much blood. Vasodilators, more blood. Local control. This is the way you send the right amount of blood to each of your tissues. And finally, just that long-term thing, growing new blood vessels. We're not going to spend much time with that, but if you have a heart attack and part of your heart, it wasn't killed, but the cells need some more oxygen, you're likely to grow new blood vessels out into that tissue. It almost acts like a bypass to try to keep that tissue healthy. If you exercise and make that tissue slightly hypoxic during exercise, it's working hard, it needs more oxygen, that will signal growth factors to cause more blood vessels to start growing. That's where you get that collateral circulation from exercise. It makes you less likely to die from a heart attack because you've got more blood vessels as backups. So if you have a tissue that needs oxygen next to a blood vessel that has plenty, it will tend to grow new blood vessels out there. And it can happen within several weeks. And finally, that's the end of the blood flow lecture.